To start out in your power hour today, we're going to talk about a little bit of vocabulary that goes along with force and motion to kind of refresh your memory on these. All right, your first vocabulary term is force. A force is a push or a pull that can change the motion of an object. Doesn't have to. I mean, you can push on something and it doesn't move. But a lot of times when things move, it's because you're pushing or pulling on them with a force, okay? Balance forces are separate forces on an object that combined do not change the movement of an object. Okay, when you think of balance forces, think of a tug of war where both sides are equally pulling on the rope. It doesn't move. So balanced forces don't cause an object to move. They're pushes or pulls that don't move an object. Unbalanced forces are forces on an object that can change the motion of the object. Okay, so think of a tug of war where one side is winning because they're pulling stronger than the other side. That's an unbalanced force. Unbalanced forces make things move. Anything that moves is being acted on by unbalanced forces. All right, the net force is the sum of all forces acting on an object. Net means sum. All right, so when you add up all the forces acting on this plane, the thrust and the lift and the drag and the weight, then you get the net force that's acting on it, that's making it fly. Okay. Motion is the change in an object's position with respect to time and in comparison to the position of other objects used as reference point. Blech, that's an ugly definition. Okay. Motion just means when you look at something, compare it to another object that is not moving, you can see that your object changes position. Like this boat right here, okay? If you look at this tent over here, while this boat is moving, the tent doesn't move because it's stationary, and then you can tell that the boat is moving because its position changes compared to that tent. Okay? That's what motion is. When something is moving, you can tell that it's moving or changing position when you compare it to something that is definitely not moving. Okay? Speed is the rate of change of position or distance traveled with respect to time. Okay, so how fast something is going, we usually call it speed. It's the rate or how much it's changing or the distance it's traveling compared to a certain amount of time. That's why when you're measuring like the speed of a car, it's miles per hour. That means how many miles did you go in an hour? Okay, that's change of position in time. A lot of other times we do meters per second or kilometers per hour. Okay, speed's always measured in a rate. Okay, Newton's law of force and acceleration. Okay, the acceleration of an object depends on the object's mass and the magnitude of the force acting on it, which is force equals mass times acceleration. Okay, all this means Newton's law of force and acceleration, you just have to remember that's the acceleration formula, which is force is equal mass times acceleration. All right? That's what's important here. How much something accelerates depends on its mass and how much force it's being pushed with. All right? And magnitude, we just use that word in the definition for Newton's law of force and acceleration. Magnitude is the size or the quantity or something. The magnitude of the force means how much you're pushing on it or how strongly you're pushing on it. All right, magnitude is the size of something. All right, and finally, acceleration is the rate of change in an object's speed. Okay, accelerating can be slowing up or slowing down or speeding up. Okay, either one. But it's how much the object's speed is changing, not how fast it's going. Okay, accelerating means the speed is changing. Okay, speed is a constant thing, but acceleration is changing speed. All right, now take a look at your vocabulary matching page, and based on what you just learned about these definitions, please match the letter of the definition on the right to the definition over here on the left. If you need to, back the video up so you can see the definitions again. You might notice these definitions are a little bit shorter than most of the ones in the video. That's because I've shortened them just to the important points.
All right, guys, we're going to take a look on this page. We're going to start at the top, and we're going to calculate unbalanced forces. So something you need to know is if the arrows are working in the same direction, then we're going to add. We'll add their forces together. If they work in opposite directions or different directions, we find the difference, which means we will subtract. So different direction means to subtract. Okay, so let's take a look at number 1. The first thing I want to point out is your up and down arrows. All right, are these working in the same direction or in opposite directions? Well, this one is going down and this one's going up, so those are opposites. Opposite directions tells us that we need to subtract. Well, if we look, they're the exact same numbers, so they're just going to cancel each other out. Okay, so now we're going to look at our left and right arrows. Are these going in the same direction or opposite directions? Well, this one's going to the right and this one's going to the left. So those are different directions. We're going to subtract. Okay, and this one is our larger force, so we know that it's going to move in that arrow's direction. So we know our direction is to the left. Okay, and so we're just going to subtract 10 newtons minus 5 newtons equals 5 newtons. So our force is 5 newtons in the direction of going to the left. All right, we're going to do the same thing for number 2. All right, first thing I notice are these 2 arrows. They're working in opposite directions. Opposite or different directions tells us that we're going to subtract, and they are the same number, so that means they're just going to cancel each other out. Okay, these 2 arrows are working, one going down, one going up, so that's opposite directions. Okay, so opposite directions, different directions, we subtract. This is my larger one, so our direction is going to be going up. And I need to subtract 10 newtons minus 5 newtons, again, is 5 newtons. So I write my force of 5 newtons. Okay, teachers, so I want the students to do problems number 3 and 4 on their own. So you may go ahead and pause the video and restart it when you're ready to check them. Okay, so number 3, to work it out, we can start with our left and right arrows. They are working in opposite directions, so we're going to subtract. All right, so we have 7 newtons minus 2 newtons. And that's going to equal 5 newtons, and this was our larger arrow, so it's going to be moving in that direction to the right. And our up and down arrows are balanced. They're pushing in opposite directions and they equal, so we don't need those. So our direction is to the right. Our force is 5 newtons. Okay. On number 4, we can start with the left and right. They're working in opposite directions again, so we're going to be subtracting. Our bigger force is this one, so we know it's going to be moving to the right. Okay, so 10 newtons minus 5 newtons equals 5 newtons. All right, and then our up and down arrows, those are also working in opposite directions, so we're going to subtract them. This one is our larger arrow, and again it's 10 minus 5, so it's an upward force of 5 newtons. Okay guys, so turn your page. We're going to work on these problems together. Number 1, which of the following conclusions is based on the data in the table? And it shows you a table with balanced forces and unbalanced forces. Okay, some things to notice is that these 3 under balanced are working in opposite directions. These two are working in opposite directions as well. These are in the same direction, and these are in completely different directions. Okay, so let's take a look at our answer choices. Letter F, there is no pattern between balanced and unbalanced forces. This word right here, no pattern, all of these are working in opposite directions, so that would be considered a pattern. That can't be it. Okay, letter G, balanced forces are equal and opposite in direction, while unbalanced forces are different sizes in the same or opposite direction. We did say that all of these are working in opposite directions, and their numbers are equal, so that part is true. Unbalanced forces are different in sizes. They can be. In the same or opposite directions. That could be correct as well. So let's keep going. Forces are always equal and opposite in direction for both balanced and unbalanced forces. This is untrue because they are not always going to be in opposite directions, especially for unbalanced. So that one cannot be correct. Okay. And then letter J, balanced forces are different sizes in the same or opposite direction. Well, all of these arrows are of the same size, not different sizes, so that one is not correct. Our answer is answer choice G. Okay. Number 2, which example does not exhibit unbalanced forces? Well, not unbalanced tells us that we're looking for something that's balanced. Okay, so looking at the first answer choice, these two arrows are working in the same direction. When they work in the same direction, we said that you add them together. That will not make this equation balanced. Okay, these two are working in opposite directions, but they're not of equal forces. So they're not equal. So that one can't be balanced either. Okay, this one, letter C, the arrows are working in opposite directions and their values are equal. So it's equal and opposite, which means those are balanced. But let's check our last one to verify. These are working in the same direction, we add them together. So it can't be letter D. Must be answer choice C because they're equal and in opposite directions. Number 3, a car runs out of gas at a red light and someone begins to push the car forward with 10 newtons of force. The force of friction is 3 newtons. What happens to the speed and direction of the car? Okay, so the first thing you need to know is, does friction work with them pushing the car forward or work against them moving the car? Friction moves against it. Okay, so we know that the car is being pushed forward at 10 newtons and that friction is working in the opposite direction. So friction is working opposite. That means we subtract and we will have 3 newtons of friction. So 10 minus 3 newtons is 7 newtons. Okay, so looking at our answer choices, does the car move forward with 10 newtons? Well, we know it's not 10 newtons. The car will move forward with a force of 7 newtons, possibly. The car will move backwards with a force of 10 newtons. That's incorrect. It's not going to move backwards, and it's not 10 newtons of force. Or will the car move backwards at 7 newtons? Well, we know again it's not moving backwards, so our good choice is letter G. Okay. Question number 4. Forces are acting on a box in all 4 directions. Which direction will the box move? So, if you notice, there's no numbers in the answer choices, so we're just looking for the direction. And we know that a larger force is the direction that it's going to go. So if we take a look at our left and right arrows, which one is larger? This one's larger, so it's going to mean we're moving to the left. And our upward and downward forces, the upward force is our larger force, so we know our box is going to move up and to the left. So that's answer choice J.
Okay, turn the page to this one with a formula triangle on it. We're going to use an FMA triangle to find either the force or the mass or the acceleration in these problems. Okay, the formula for calculating force is force equals mass times acceleration, where F is force in newtons, M is mass in kilograms, and A is acceleration in meters per second squared. And this is how you set it up. The force goes on the top because force equals mass times acceleration. Okay, and it's always the two in the bottom that are side by side that you multiply. This formula, force equals mass times acceleration, will be on your star chart, but your triangle won't be. So remember how the triangle works, and then when you see the formula on the star chart, you can draw the triangle right next to it. Okay, let's try this in one of our problems here. Okay, number 1 says, with how much force must a soccer player kick a 2 kilogram ball if she wants it to accelerate at 12 meters per second squared? Okay, so we are looking for how much force. So we are going to be looking for F for force. Okay, we already know that the ball is 2 kilograms, and if it's kilograms, it's mass, and she wants it to accelerate at 12 meters per second. That's our A for acceleration. Okay, so let's put these in our triangle. We don't know force, so we'll put an F there. We know our mass is 2 kilograms, and we know our acceleration is 12 meters per second squared. Okay, what does our triangle tell us to do? It tells us that force is going to be equal to 2 times 12. Okay, so I'm going to write that out. Force equals, my mass is 2 kilograms times 12 meters per second squared is my acceleration. Okay, I'm not even going to do the math on this one. What's 2 times 12? That's 24. So the force is going to be 24 newtons. Okay, let's look at our second problem. What is the mass of a model rocket that accelerates at 50 meters per second square with a force of 150 newtons? Okay, mass we don't know. Our acceleration is 50 meters per second squared, so that's our A. And then it says right here our force is 150 newtons, that's our F. Okay, so we know the force, 150 newtons. We do not know our mass, so that's going to be just an M here. And then we know our acceleration is 50 meters per second squared. All right. This time, since they're on top and bottom, we have to divide, and there's a little division symbol right there that tells us that. So the mass is going to be equal to 150 newtons divided by 50 meters per second squared. All right, so we have 150 divided by 50. All right, how many times will 50 go into 150? 3 times. 3 times 50 is 150, so you have nothing left over. So our mass is equal to 3 kilograms. Okay. Every time when you're using mass in this formula, it's always kilograms. All right, let's do our final one. What is the acceleration of a 2,000 kilogram car that is pushed with a force of 1,000 newtons? All right, we don't know acceleration. That's A. 2,000 kilograms is our mass, and force F is 1,000. Okay, so acceleration, don't know. The force is going to be 1,000 newtons, and the mass is going to be 2,000 kilograms. All right, so my acceleration is going to be, since they're on top and bottom, I have to divide 1,000, and I'm going to write it like a fraction this time, top and bottom, and you'll see why in a minute. 1,000 newtons divided by 2,000 kilograms. Okay, this one, instead of doing this ugly division, let's just simplify our fraction. Look at this. You can cross out your zeros, and your acceleration is equal to 1/2 meter per second squared. That's it.
Okay guys, turn your page. We're going to work through these problems using our triangle. Yes, you must write your triangle and fill it in correctly. Number 1, if a 5 kilogram ball is accelerating 1.2 meters per second squared, what is the force on it? Okay, so we know that 5 kilograms is our mass, and 1.2 meters per second squared is our acceleration, and we're looking for the force. So we draw our triangle. Okay, force is what we're looking for. It's on top. And then we have our mass and our acceleration. And when they're side by side, we multiply. So 5 times 1.2. 5 times 2 is 10. Carry your 1. 5 times 1 is 5. Plus 1 is 6. And we have 1 decimal place. So 6.0 newtons is our force. All right. Question number 2. What is the mass of a student in a rolling chair if pushed with a force of 90 newtons and accelerates at 3 meters per second squared? So we're looking for the mass. We have a force of 90 newtons and acceleration of 3 meters per second squared. So we take those numbers, we plug them into our triangle. Our force on top is 90 newtons. Mass is what we're looking for, and our acceleration is 3 meters per second squared. Top and bottom, we divide. So 90 divided by 3. 90 divided by 3. 3 can go into 9 3 times. 3 times 3 is 9. We subtract and get 0. We have to bring down our 0. 3 will go into 0 times. 0 times 3 is 0, and we have finished. So 30, and remember our units for mass are kilograms. So 30 kilograms. Okay. Question number 3. What is the acceleration of softball if it has a mass of 5 kilograms and hits the catcher's glove with a force of 100 newtons? Okay, we're looking for acceleration. We know that the mass is 5 kilograms and the force is 100 newtons. Okay, we draw our triangle and we fill it in. Force on top, 100 newtons. Mass of 5 kilograms. And we're looking for acceleration. Top and bottom, we divide. 100 divided by 5. 5 can't go into 1, but 5 can go into 10. 2 times 5 is 10. We subtract and get 0. We bring down our 0. 5 can go into 0. 0 times 5 is 0. And we're done. So for acceleration, we have 20 meters per second squared. Okay? Now, for question number 4, it says, students in a science lab performed a series of controlled experiments on 3 carts of different masses. The students' results are shown below. And then you have your data for cart A, B, and C. And it says, based on the recorded observations, which cart is capable of an acceleration of 20 meters per second squared if 800 newtons of force is applied to the cart? Okay, so what we're looking for is to get to that 800 newtons. So if we go back to our charts, right here we have 80 newtons of force. Well, what do we have to do to 80 to get to 800? Hopefully you say multiply by 10. Okay, but if we multiply this by 10, we have to multiply over here by 10. What we do to one side, we have to do to the other. Okay? So this, our force now becomes 800, and our acceleration, 2.0, or 2 times 10, is 20. Okay? We can do the same thing for cart B. 80 times 10, that's going to give us our 800, and 1 times 10 is going to be 10. Okay, that's our acceleration if our force was at 800. And the same thing for cart C. To get 80 to 100, we multiply by 10. What we do to one side, we do to the other. So 8.0 times 10 becomes 80. All right, so now we know if we were at a force of 800 for each cart, we know what their new accelerations are. All right, so let's look at our answer choices. It says cart A at 40 kilograms because increasing the force applied to 800 newtons will increase its acceleration to 20 meters per second squared. Well, when we did 800, our acceleration is 20, so that one is correct. Let's keep looking. Cart B at 80 kilograms because increasing the force applied to 800 newtons will increase its acceleration to 20 meters per second. Well, for cart B, we had 800 for our force and only 10 for our acceleration. So we can eliminate answer choice B. Okay, which also allows us to eliminate answer choice D, all of the above. So we just need to verify that cart C doesn't work to know that cart A is correct. So cart C at 10 kilograms because increasing the force applied to 800 newtons will increase its acceleration to 20 meters per second squared. Well, at 800, cart C acceleration is at 80, not at 20. So we know that answer choice C is not correct, leaving answer choice A.
Okay, now you turn your page to the practice questions. There's 6 practice questions. You're going to work through these on your own or with a partner. And toward the end of the power hour, your teacher's going to turn the video back on so you can see the answers and check your work. Okay?
Okay, let's take a look at your responses and check that you got the correct answers. On number 1, it's talking about student number 1 pushing the object to the left at a force of 10 newtons and a friction force acting against it of 4 newtons. So if they're working in opposite directions, we're going to subtract. So we do 10 newtons minus 4 newtons equals 6 newtons. That's answer choice G. Okay. Number 2, in this question, you were calculating out the acceleration. So you use your triangle, you fill in what you know. We know that the force is 10.8 newtons and the mass is 0.60 newtons. Okay, so we have to divide. The top number goes inside, the bottom number goes outside. We can't divide by a decimal, so we have to get rid of it. We move it 2 places over to get it to the end. What we do on the outside, we have to do on the inside. We have to move the decimal 2 places over. So whenever you calculate it out, your answer is 18. Question number 3. It wants to know which cart's going to have the greatest change in speed. Well, in this question, change in speed is talking about the acceleration of the cart. If you think about it, if you were to push each of these carts the same way, would a light cart or a heavy cart move faster? Well, it's easier for us to move something that's lighter, so we look for the cart with the smallest mass, and that is answer choice A. Question number 4. To help myself, I wrote out the data from the table onto my picture, and I noticed that my speeds are increasing, so I can eliminate answer choice F and J. That leaves me G and H. The reason G is incorrect is because it's talking about the force acting on the cart is greater than the force of gravity. Well, gravity in this case is actually helping because our cart is going downward. So that is incorrect. The correct answer is answer choice H, because it's talking about the cart's speed increasing as it goes down the ramp, and because the forces acting on the cart are unbalanced. Remember, unbalanced means that it's moving. Okay, question number 5. On this one, to calculate your numbers from your chart, we have the force and we have the acceleration. To get the difference between them, if we multiply each of these numbers by 0.2, it gives us our acceleration. So we're trying to find our missing piece. So what times 0.2 equals 2.6, which is our number on this side. Okay? Again, whenever we're dividing by decimals, we can't have a decimal out here, so we have to move it one place to get it to the end. So what we do on the inside, what we do on the outside, we have to do on the inside. So 26 divided by 2 is 13 newtons. F is the correct answer. Question number 6. It's talking about this boat moving up a river, and the boat has a force of 3 and a current working against it of 1. All right, so they're unbalanced, meaning the boat moves forward, and it wants to change the force working against it to 2 instead of 1. So more force is pushing against the boat going forward. All right, so answer choice F is our best answer because the boat will move slower but still going forward. That's because we added more force working against it, so it's going to be harder for it to move forward. All right, the rest of these we can eliminate because it's not going to help the boat by adding more force working against it. It will not stop the boat because the forces are not equal, and the boat will not move west because there's not a force pushing it to the west.